Hello, everyone. Thank you for joining this new session of our Cloud Native New York meetup. Today we have with us Adrien Guillo. I hope that I didn't butcher your surname. He is co-founder and core contributor for the solution that we're going to talk about today. The company is Quickwit, and they have a new approach to search for log and management and analytics around the topic. So if you are looking for an alternative for Elasticsearch, you want to listen to this. And Adrien.
Thanks, Gabri. Yeah, so I'm Adrien Guillo. You did not butcher my name. I've been working on Quickwit for 2 years now. It's an open source project that started in 2021. I'm a software engineer with a decade of experience. And my last job at a software company was at Airbnb, where I was working in a data infrastructure team working on their data warehouse. But today we're not going to talk about data warehousing. We're going to talk about search engine. I want to talk about Quickwit, but especially the novel architecture that Quickwit uses to offer a cloud-native search engine for distributed tracing, log management analytics. And in general, Quickwit is a good fit for everything that's immutable. So when you think about immutable data, obviously you think about logs, but it can be basically any events that once it's sent, it's not modified. But you also can think about emails, text, conversation data is a really good use case for Quickwit. Quickwit is built on top of a indexing library called 10TV that was also created by the founders of Quickwit. It's a library written in Rust, and it's the equivalent of in the Rust world of what is Lucene in the Java world. So almost all the search engine in the Java world, so Elasticsearch, OpenSearch, Solr, are built on top of Lucene. And so 10TV is the equivalent of Lucene, only written in Rust and on average twice as fast. But what's really different about Quickwit is the first search engine to decouple storage from compute. So what does that mean? I feel like it's been a buzzword for the last few years. Everybody wants to decouple storage from compute. And so it's a trend that started in the data warehouse space. Snowflake made it really, really popular. So I feel like when we say decoupling storage from compute, a lot of people think about Snowflake, but actually like some other companies moved their data warehouse to S3 before Snowflake did. I'm thinking about, in particular, about Netflix. So like the name implies, it means that you compute and storage are no longer tied together. So you have a storage layer that can grow independently from the compute layer. And basically it boils down to adopting a new architecture. And that architecture is sometimes called stateless, sometimes called shared disk architecture. And so today, basically most of this presentation is about what is shared nothing, the architecture where you don't decouple storage and compute. What are the pros and cons of that architecture? And what is shared nothing, shared disk? And same thing, what are the pros and cons? What allows you to go from one to the other? So first, I'm gonna talk about shared nothing architecture. The name maybe doesn't ring a bell for you, but actually, if you work in software engineering IT, you use a lot of systems that adopt this architecture. And so we said that a cluster, an architecture is shared nothing if the cluster is composed of nodes that are independent from each other. They don't share resources. Because they don't share resources, you have no bottlenecks. You don't have contention trying to access the same resource. So that makes them usually pretty scalable. So the nodes do not share the same processor, the same memory or storage. They're only tied together, linked together through the network. And so in that world, data sets that you want to host, work on, are divided in smaller chunks of data, and each node is responsible for a piece of the data set, usually called a partition or a shard. Some backends use different names, but mostly we talk about partitions and shards. And so the data set is divided into chunks, and the computations are divided also in smaller units of work, usually called task. And examples of such systems that use that architecture are, I think, Hadoop in general with HDFS for storage and might be used for computation, but also Cassandra, Elasticsearch. This is a very ubiquitous architecture, and for good reason. All right, let's see. So I'm gonna take a particular example for Elasticsearch, since today we're gonna talk about search engines. So Elasticsearch decompose the data set. In the search world, the data set is called an index because the underlying technologies like search inverted indices. So we call the data set index. It's composed of many records, logs in search. We call them documents. You divide your index into shards. Shards are replicated for fault tolerance and scalability. So if you look at a diagram, it just looks like this. Horizontally, you split your data set into shards. Vertically, you have replicas of the same shard. And each node uses its own CPU, its own memory, its own storage to work on the shard. And so it's great for fault tolerance. If you have multiple replicas, you can afford to lose one replica and you're still able to serve queries. So the number of replicas that a shard is called the replication factor. So the minimum, usually the minimum you want is 2, very often 3, more rarely 4, but that happens. So that's, yes.
Adrien, I just wonder, can you speak a little bit to the difference between partitions and shards?
Those are usually the same. So you could use both in and interchange them. Like some backends, they decide to use the word shard. Some backends, they decide to use the word partitions. But really, that means that it's a subset of the data. And so you have your big data set that you want to manage with different nodes. And to do so, you divide your data set in small pieces. And the small piece is called usually a partition or shard. So so like replicas is for fault tolerance. You add replicas so you can lose nodes without losing data and keep serving queries. Or you can also add shards in the eventuality of adding data. So if your data set is growing, what you can do is just add more shards, more nodes and more shards usually. So that's the topology of your cluster. So if you do search and you issue a search query, what happens? Usually a node in the cluster that is usually called the root node or the coordination node is being hit first with the query. And that node, what it does is it forwards the query to each of the replicas in the cluster. So in that instance, so we want to hit all the shards, and we can hit either replicas. So in that example, let's just say you have a query that would hit the shard 1 replica 1, shard 2 replica 2, and shard 3 replica. Oh, there's a typo. It should be replica 1. So each replica is going to answer the query locally, find the result locally, answer the root node, and the root node sometimes is going to do some post-processing. So the most simple one is just like it's going to concatenate all the results. But maybe you asked to rank the results, So each replica is going to respond with partial results that are sorted, and the root nodes or the coordinator nodes still need to apply a final sort to those intermediate results to answer with the final result. So the search path is the read path. This is where you query data. There's another path called the write path or indexing path. And usually those systems expose some sort of API where you push data. You're going to hit usually a coordination node, and that coordination node, depending usually on some ID of the data, is going to identify through a hashing algorithm, usually a consistent hashing algorithm, or sometimes a rendezvous hashing algorithm. It's going to determine which is the right shard. So once the shard for the document is found, it's going to forward the document to each replica, and each replica is going to index locally the document and add it to the index. So that's nothing architecture in a nutshell. So the advantages of nothing architecture is fault tolerant. As long as you can replicate the data, you're fault tolerant. It is scalable. You can always add more nodes to handle more partitions. And because there's nothing is shared between the nodes. There's no, like I said before, there's no contention, so it scales pretty well. The only problem you can have is hotspot, which sometimes a partition is basically more popular than the others. In that case, you have to find a clever partitioning mechanism. But if you don't have hotspot, if the load is evenly spread out, it's a very scalable architecture. What's really great also is the data does not move. Only the query, which is small, and the result sets who are small too move. So you don't move much data around. Time to search is really good. So time to search is the delay between the moment the data was added and the moment the data was queried, because you hit nodes locally and they work on SSDs. And everything is everything is in memory. You can add the document pretty quickly to the index. And for the same reason, because everything is there locally, and you know that because of the partitioning mechanism, you know that all the versions of the documents are on the same partition. You know that if you mutate the same document, you just have to work on just one partition. So it's also a good architecture for mutability. So the cons now, a big one. And that's why a lot of companies are trying to move from nothing architecture to shared disk architecture when the system is compatible with it. Since you can't scale the storage and compute independently, it's really hard to optimize utilization. So I'm gonna take an example. Let's just say you work on a large data set, and for compliance reason, you need to keep 1 year of data. Assume you decide, okay, for each day, I'm going to do one partition. So you have 365 partitions. So your cluster needs to be as big enough to handle all those partitions. However, maybe internally, most of the queries are interested in the last 24 hours, or even let's say the last week. What that means is basically only seven shards, so maybe 14 replicas, or 21 replicas if your replication factor is 3. Yeah, so in that example, storage is going to be very well utilized. You can optimize the amount of space you have on your disk, so that the amount of space on your disk fit the size of the dataset. However, you're still going to have on each of those machines that are queried, basically, you're still going to have CPUs and memory that's basically not going to be used. So that's the main reason why people want to scale, decouple storage and compute so they can optimize utilization. Another cons of Shared nothing architecture in this Elasticsearch example is you need to index on each replica. So that basically wastes some CPU. You're doing the same work. So if your replication factor is 2, you index the same documents twice. If your replication factor is 3, you index your document 3 times. So you waste a little bit of CPU there. Another thing is indexing and search happen on the same machines, but usually they have like different properties. Like for indexing, maybe you want like really beefy CPUs and disks, whereas on the search front, maybe you can fit everything in memory, so you don't need to have like those very, very large disks. If you have coupled storage and compute, it's really hard to specialize their hardware for the different use cases. And another kind of shared nothing architecture is like the operational complexity that can come with decreasing or increasing the number of shards. If you Google adding shards, Elasticsearch, or adding nodes, Cassandra, there's a bunch of like blog posts that tells you how to do it, because usually it leads to operational complexity. Because it's not as straightforward, your team needs to be trained to do that operation smoothly. And because networks are getting faster in the last 20 years, shared disk architecture has gotten traction, especially with the availability of cloud storage. So what is shared disk architecture? It's at the end of the day, it's pretty simple. You have like a storage tier that's responsible for storage, and a compute tier that's responsible for compute. And now you can scale them independently. You can specialize the hardware independently. So I could have played with the diagram and like maybe put like some SSDs on the CPUs and maybe a lot of memory on the compute. Also, elasticity becomes like easier. Like let's just say like you have like different teams that have like different compute needs in your company. Maybe you have like a data scientist team, and they need GPU power. Maybe they can have like a small compute cluster with GPUs for that. You can even shut it down maybe during the weekend if they don't use it without impacting storage. And maybe you have another team that's doing some other kind of computation that needs maybe to be a bit more snappy. So you give them like maybe better networking capabilities, that kind of thing. So with that architecture, it's much easier to adapt the hardware and the clusters to the workload particularities.
You were saying, sorry, Adrien, that if you the example you gave of shutting down compute while people like separating storage and compute, and you can shut down the compute, would that be sort of motivated by cost savings?
Yeah. Okay. Usually it's motivated by cost saving or like efficiency. But like if you come back to that example, and like all your data is on disk. Like let's just say you are, I don't know, your B2B business. So your app is mostly used during the week and barely used during weekends. You have no way to shut down your cluster during the weekend because the data is on the cluster. If you shut down the cluster, you shut down you lose your data basically. If you have this architecture during the weekend, you can, if nobody's using the compute, nobody's doing queries, nobody's using your app, maybe you can just like reduce to the minimum your compute layer and still keep the storage around. But it's a much more elastic way to do things. And so the pros is, I guess I've been repeating myself for the last 10 minutes now. And the pros is like you can scale independently, you can use dedicated hardware. The cons is usually increased complexity. You know, you have like 2 tiers that you need to manage. The network bandwidth can become a bottleneck, and now you have like extra network latency. Before, the data and the compute are located in the same space, so there's no latency. Like the computation has the data readily available. There's no transfer, so there's no bottleneck through the bandwidth, and also there's no added network latency. The operational complexity, there's a way around it. It's cloud object storage. Like in the cloud world, when you use I don't know, Amazon S3 or like Azure blob storage, you don't have to deal with the complexity of managing the storage at all. You're dealing with the serverless API, and it has the nice benefits of scale almost infinitely. Usually, cloud storage is very, very cost efficient. Maybe you have like a really good operations team at your company, but it's still pretty hard to achieve the durability and availability that the cloud providers offer. So you get that for free, and then cloud storage usually have like some nice features that you're gonna get for free, basically. So they have like storage classes. So those are classes that allow you to save money on data that you don't access very often. You also have like cross-region replication. So you can replicate your data pretty easily to like other geographical areas. So that's something that's really non-trivial to do if you're hosting the data yourself. And if you're using cloud storage, you only have to click a few buttons in your UI interface, and you're done. You have like replication for free, for instance. The cons are similar though. Like the network bandwidth is still a bottleneck, and you still have an extra network latency. So it seems like shared disk is the new panacea. It's magic. It allows you to scale your tiers independently. You have like better durability, better availability. So it feels like everybody should and could do it. But it's a bit more complicated than that. Because of the network that's in the middle of your storage and your compute, you have to relax the latency constraints, the throughput constraints, and only a few systems that have like IO access patterns can actually afford to move to a shared disk architecture. And so the reason Quickwit is able to decouple compute and storage is because we were able to relax the constraints on latency, throughput, and also like make sure the IO pattern allow for using that architecture. So let me explain in more details. So relaxing the latency constraints. Every time you go to cloud object storage, you pay, depending on your provider, a round trip is between like 50 and 100 milliseconds. Sometimes when you're lucky, like the P50 latencies are pretty good. So you're around 50 milliseconds, sometimes below, but like the tail latency can be quite high. So the round trip is really, really expensive. So it's really not suitable for like machine to machine low latency applications. Like every application that wants like really low latency, let's just say under 100 milliseconds, that's really not a good candidate for moving the hot data to object storage. So for search, for instance, e-commerce search is an example of applications that you don't want to move your data for e-commerce search to S3, because it's been proven that after, I think it's 300 or 400 milliseconds, you actually start losing revenue when the search experience is really not snappy. So there's just no way you're gonna move your data to cloud storage for that kind of application. But there are some applications where it's totally fine. We call them like human to machine applications. So all the observability use cases, the security audit use cases, when you have a human that's willing to wait for like, I don't know, 300, 400, 500 milliseconds, maybe a second, that experience is, I'm going to say like bearable. And so now you can actually think about using object storage, because now the latency, you can expect a latency in like a few hundred milliseconds using object storage. So that's what we do. We say, hey, Quickwit uses object storage. Be careful for which use case you use it. Like, just don't do e-commerce search with Quickwit. It's not a good use case. For the other use cases, go crazy. Now you also have a throughput constraint. If you look at the throughput of one connection to A3, we measured it and we said our mental model at Quickwit is basically one connection is about 100 megabytes per second. So S3 feels pretty slow, like basically like a slow spinning disk, but it's definitely not like an SSD. And so you can see where you're at on the diagram between throughput and latency. So pretty low throughput, pretty high latency. So not great. However, what we can do with cloud storage is, because behind the hood, your data is hosted by many machines, and they're pretty good at load balancing. You can go crazy and you can issue like a lot of queries in parallel, and you can issue like 10, 15, 20, even 30, maybe even more queries in parallel. And so now you can achieve a much higher throughput using parallel requests. So latency is still going to be great. Like the latency that's still non-negotiable, but throughput can be really improved. So in a Quickwit use case, we make sure we plan the IO operations ahead. That means that you can't afford to start a request, wait for it to come back, start a request, wait for it to come back, and do it 30 times. What you have to do is, like, in advance, be like, plan your IOs and say, okay, to do this computation, I'm gonna need like 25 requests. And so as soon as the query arrives, you need to plan those requests so that they can come back in time. So we plan the IOs so that they run in parallel and they run asynchronously. And finally, you have to have a compatible IO access patterns. And I think that those, like the next few slides, are actually the most important slides of the presentation, because they explain how we do what we do and why we're able to do it. So as I was saying in the beginning, the indexing library that we use is called 10TV, and so a piece of index is called a segment. And so if you trace the IO operations that are done just to open a 10TV segment, not even to perform a computation, get data from the segment, but just open it, and you trace that if you could do it on your local machine, you realize that just to open the segment, a 10TV segment, you issue 28 reads and you download like very little data, 34 kilobytes. So because it all happens on your SSD, like, and each read takes like nanoseconds, you don't realize that this is happening on the road. But now you imagine you put your 10TV segment on object storage, you would have to multiply basically 28 by 100. So we take 2,800 milliseconds to open your 10TV segment. And that obviously wouldn't work, because then on top of that, you would have to download the data, get it back. So what we had to do is use something a little bit different. So it's still based on 10TV, but we have a structure on top of it that we call the turbo index, that basically wraps a 10 TV segment, and that is basically pre-computing all the data that you're going to need for opening the 10 TV segment. So when the split is on object storage, instead of going there and asking for data 28 times, we only go there one time and we get a tiny piece of data, and now we have everything we need to perform the computation. So that trick, we do it for opening the index, and we do it in a few other places to minimize the number of requests that we need to do to object storage to answer such a search query. So we use an index format that minimizes the number of random IOs, and we're able to answer a search query in at the minimum 3 requests. So that's why we're able to answer in less than a second, because like worst case scenario, each request takes 100 milliseconds by 300 milliseconds. It takes more time than that, because we still have to like download some data and then process it. So use some compute. So obviously it's gonna take more time than that. But the reason we're still able to do everything in less than a second, and sometimes more, like if there's too much data, we'll take 1 second, 2 seconds, even 3 seconds if the data set is large and we don't have enough machines of bandwidth. But the only reason we're able to do so is because we're able to pre-compute and minimize the number of IOs that we do to object storage. So since I presented Elasticsearch nothing architecture, I wanted to show what it looks like in the Quickwit world. So same thing, the data set that we call index is composed of many documents. The index is divided into splits. So Elasticsearch decided to use the chunks, shards, we call them splits. So what we do is the data arrive through the API, we compute the index, and then we upload it to object storage. And then on the other side, we have like stateless search nodes that query the split straight from object storage. So I have a diagram here. So the same document arrives, it goes through a distributed queue. That's a pretty old diagram. We actually do have like a ingest API the same way Elasticsearch does now. We emit a split every 30 seconds. So that's one of the limitations that we have. Like for Elasticsearch, since they're working on local SSD, it's really easy to write data very often. It's not convenient for us to write data to S3 every 500 milliseconds. So we just have to wait 30 seconds. We could do 15 seconds, but not much less. We have to wait a little bit to accumulate enough documents, and then we upload the data to S3. So our time to search is not as good as that of Elasticsearch. And then when we have uploaded that split to S3, we have a metadata layer that we update, and we say, hey, there's a new piece of data available. And then on the search path, we still have that notion of root node. So when your query arrives, you go to root node. The root node goes to the metadata layer. The metadata layer tells you what are the relevant split for your query. And then we go to each leaf node. They work on a subset of the data. They work on a subset of splits. They go to S3, they get the data they need to answer the query. They do the computation, and then they answer the root node. The root node may or may not perform some additional aggregation, and then your query is returned. So the pros of this architecture, we are more CPU efficient because we only index the document once. We're usually more cost efficient for several reasons. So one, because we're more CPU efficient, because we use cheaper storage, like S3 is just cheaper than SSDs. Another reason is elasticity. same thing. Like if your application doesn't need search over the weekend, you can just shut down your searchers, and the data remains on S3. It's because the nodes are stateless. It's really easy to remove and add nodes in a few seconds. So that produces with like greater elasticity, which translates to like better utilization, and basically you get a better bang for your buck. So you use the cloud more efficiently. So that's why we say that Quickwit is a cloud friendlier than Elasticsearch. I'm not saying that Elasticsearch is bad. It still runs in the cloud and it runs great. It runs great. And if you're doing e-commerce search, you should use Elasticsearch or any low latency system. But for other use cases, you may benefit from great cost saving, but maybe using a system like Quickwit. And last but not least, operational burden and complexity is also reduced because basically you're using object storage. So once again, you get the availability, durability for free. The cons, like I said, incompressible query latency of 300 to 500 milliseconds, time to search of 30 seconds, and finally, slow mutability. So we are able to support deletions only at a slow rate, and we support it just for like compliance reason. The reason is like our data, our splits, they are on S3 and they're pretty big. So if you want to modify one document in there, you have to rewrite the whole thing. So it's really not great if you have like a really high rate of mutations. But if like I think GDPR it's gives you like maybe 60 days to get rid of the data. So if you do like a huge batch of deletion every 60 days, then we can handle it. If you do mutations every hour or every minute, this is not going to be a good use case.
I feel like you're describing how every time I unsubscribe from an email list, it takes them 30 or 60 days. They don't like to delete either.
Yeah. Deletes have been like an afterthought for a long time for like many systems. And so very often it's a second class citizen. Because like when you design a system and you know that the data is immutable, or you force people into dealing with immutable data, then you can take shortcuts, so you can design things differently the way we're doing it with Quickwit. If you add deletions after the fact, it becomes much more trickier. So I have a small demo. Yes. So I feel like Quickwit, and at the end of the day, is an API, so that always makes for like very underwhelming demos. So here we have a data set. So this is the Quickwit UI. I am running a Kubernetes cluster in our demo environment. So I connected to the UI, and the UI have one data set, one index that's from GitHub Archive. GitHub Archive is it's this data set. It's a public data set where all the events of GitHub are available. So it's a pretty cool data set to work with. It has like a lot of data. It has a lot of text data, which is pretty good for Elasticsearch. So unfortunately, there was some miscommunication with my co-founder, and he scratched the index a few hours before I was supposed to present. So that index is not that big. Unfortunately, we're not in terabytes. I think we're close to 1 terabyte. It's still indexing. So that's that's one document. So let's do a search with my login. We don't have that many hits because we only have like I think a few weeks of data in there. I think there's like 350 million documents last time I checked. So I guess in the last events that in Dataset, my login came up 858 times. And so you can see that here, I probably opened an issue on the Quickwit repository. What did I do here? Yeah, nothing interesting. So obviously it's search, so you can search for text. So I probably say shoot very often in my issues. So I can run the query, and in a bit less than a second, there are 26 hits where I used found. We don't have highlighting, fortunately. Like I say should. Yeah, it should be possible to define them in a Quickwit config, so on and so forth.
Does it support wildcards or regular expressions?
No, yet we could. We are working on it on the roadmap, but we don't have wildcard expressions right now. What we have is what we already have is, for instance, they're like really specific to search, is like phrase queries. So if I say should be, it's not only gonna verify that you have should and be in the document, but it's gonna verify that they're both one after the other. So if I search for should be, I had how many hits before? Yeah, I had 26 hits, and now I just have 10.
Mm-hmm.
So that's an example of and so in the next it's still a young project, so we like a bunch of feature, but the indexing technology 10TV has regular expressions, so we should be able to plug a regular expression quickly now in Quickwit. So yeah, should be there. So what I want to show now is how it's basically reading from history, because now you could say, hey, everything is in a cache. It's fast because you're not going to S3. Because yeah, the first query, like we eat S3, and then we're not totally crazy. Like our machine, they still have like small SSD or bit of memory, so we cache some data structure. So the following queries are faster if you want them to be. We have some different caching settings. But what I want to show is, can you see my terminal?
Yes.
Yeah. Before I just one more question on that last screen. So what you're searching right now is like JSON.
Yes.
But like what other structures do you support?
We only support JSON right now.
Okay. So
we don't support CSV. We don't support protobuf, Avro. We only have one first-class citizen, and it's JSON. And we could add it in the future. We don't have that. We didn't have that many requests for other file formats actually.
Mm-hmm.
So I was thinking, like in here we are talking about searching logs in the sense that these are information that are immutable, that happen, like events, whatever it is that we want to call this. I imagine that if I'm working, for example, in social media, I wanna implement a query to see all of the likes that I did in my Instagram, for example. All this would be an appropriate use case. Yeah,
if every like is an event and the event doesn't change, yeah. And then we also support aggregation, so you should be able to do a sum of likes. So we do support that use case.
So in this sense, every time I can collect information for my system in the form of an event that happened at some point, and I want to do a search on it, like that, as you were saying, doesn't require like to have a latency that is pretty short. That's a good use case for something like this. So there are actually a really wide number of situation, just because when I was looking, reading the abstract and I was reading logs, I wasn't really sure. But in reality, it's not like just log in the sense of or a system that takes a log, is any type of activity that I can represent in that way. So even a stream of events that perfectly match the case.
So I think we have a marketing issue there. When we say, hey, Quickwit is for immutable data, I feel like it makes our messaging not super clear because not everybody knows exactly what it means. And so it becomes unclear what they can do with Quickwit. And since at the end of the day, most people are interested in their logs, their traces, I think it's just easier for us to say, hey, it's really good for the use cases because this is also where the market is. And that's why we position Quickwit this way. But like some users understand that, just not for logs and distributed tracing. They understand that anything that's immutable and that or can be modeled in an immutable way is a good fit for Quickwit.
So if you need to do a computation like this, you were talking about retail before, and of course there are situations where the response needs to be immediate, and so this wouldn't eventually qualify. But if you want to do this post facto, like collect information on your data, this is totally appropriate.
Yeah, exactly. Like you probably don't want to use Quickwit for like the search of your e-commerce, the search bar and then the items that you want to buy, because there you run really fast. But maybe all those events, you can log them and you can index them with Quickwit, and then your analysts or like your dashboard, they could be powered by Quickwit.
Correct. So exactly, I see this is really powerful to do research in collect factors, identify pattern in the data, all of this type of situation.
It's also it's really good for security use cases, because very often in security, you really have the needle in the haystack problem. You're looking for the one user, the one IP, and the problem with like technologies that don't use indexes, and basically they have to scan the whole data set to find that unique IP or to find that unique user ID. Whereas with search, there's that data structure that is the index that pre-computes the data basically and can really quickly tell you, hey, that IP, it's at that piece of data, that username. So it's really good for investigation, security, those are things.
And I'm also thinking, I know I sound like a broken record to Cora because I always mention edge use cases, but they are really a lot in my mind, and I have a lot of focus over there. For example, when you want to do some kind of post-mortem, or you need to identify something that happens, and you have all of this huge target of deployments, and you collect data from those deployments, that this also would be a great engine to use for the same reason.
Yes. So yes, I think it's our favorite use case, because you want to collect all that data and keep it, because maybe you're going to need it, but maybe not. So if you have like a pulse system, you have to pay for that compute all the time, because maybe you want to query the data. Whereas if you use a system like Quickwit that they compute storage and compute, then you can more easily tell yourself, hey, I'm going to keep that data for like 2 weeks, a month, 6 months, and maybe I'm going to use it. And then the day you actually need it, you can spin up a few searchers, or like many searchers if you have like a huge data set. And then you can you can do that forensic investigation.
That's yeah, that's great. I'm thinking in using, for example, a public cloud provider like AWS. You can store all of this in a low cost storage like Glacier, and then bring back S3 and do your job, and then move back. And this operation per se is not particularly an overhead.
No, No, yeah, you could do that. You could store the Quickwit index for, I don't know, years if you wanted to, put in Glacier, forget about it. And then, I don't know, you're in a financial institution, you have to keep all the transactions. And for some reason, like 2 years later, the SEC is like, oh, like in January 3 years ago, you did this or that, like give us the data. We need to know about person X or Y that did this, then that would be a really good use case.
Thank you.
Something I want to show is if you see my terminal, maybe I'll make it a little bit bigger.
Yeah, I see you're scaling up.
Yeah.
I mean, scaling up or down, like 0. So yeah, down.
Yeah. I'm actually going to scale down. So this is going to crash my so I'm gonna wait for Kubernetes to, so those are the pods that are running in our small demo cluster. So I have 2 meta stores. So it's that metadata layer. We have one janitor, it's the process that's responsible for doing some cleanups, basically, when you delete things around. And you have searchers. So searchers are the stateless nodes that we use for search. So at some point, yeah. So at some point, they're gonna, those nodes are gonna go away. And what I'm gonna do is I'm gonna quickly spin up 3 searchers, and then I'm gonna go back quickly in the UI and see how much time it takes for the searcher to come back up and answer the first query. And that way, I hope to convince you that the data was not on the searcher; it was uncached. It came straight from S3. So let's go back to this is broken. You can see here, failed to fetch. All right, so 3 searchers. Reopen the connection. And now I'm waiting for my nodes to come back up. So, oh, I was much faster than when I tried it before. I was expecting more like 15 seconds. Anyway, so in less than, so I don't know, it took me like a few seconds to do the whole thing. So let's say that basically like in less than 10 seconds, the node had time to come back up. They talk to each other through a gossip algorithm. So come back together and talk together, and then answer the query. And now, as I was saying, the following requests are going to be a bit going to be faster. The reason being, if you go back to my slide, that thing that we call the turbo index, that's pretty small for each split. We cache it. So the next query are going to be even faster. So if I hit another piece of data, a split that was not in my first query, it's going to be slower again. But the thing is, I think that query is hitting all of them, so it's not.
And right now, when you cache, this is a local cache. You are not using something like Redis or other mechanism.
No. This is so we have, no, we don't have actually. We will have storage tiers. So you could, right now we just use in memory. So not all of data is in memory right now. The whole data set doesn't fit memory, but some pieces, like that first piece that saves us one round trip, that's for sure in memory right now because it's only a few kilobytes. So that saves
memory in all 3 nodes.
Yeah, it's probably all 3 nodes probably.
It's
so
replicated.
It's a few kilobytes. So this one we don't download again. But the rest of the data set is not cached, and it's for sure more than the whole memory capacity of the cluster. So what we hope to do in the future is have memory cache, SSD cache. So let's say you have, I don't know, a week of data, where we could do like cache the last 24 hours on SSDs. The rest would be on S3. And so the queries on the last 24 hours would be basically almost as fast as Elasticsearch on that piece, because it would be already there. So you have the best of both worlds. You can have like size your SSDs to basically fit your hot data set, and for the long tail, you would use S3. So that's on our roadmap. It's not out yet, but it's for sure something that we have in mind.
I'd like to ask a little bit more around the caching mechanism and exactly dig deeper in this question that also Cora asked. So right now we have 3 searchers. So we have 3 different pods that are running and doing the search. So, and who is executing this query? All of the 3 nodes?
Yes.
Okay.
So
sorry, all of the 3 pods, not
yeah, the three pods. So we have, for the data set, we have many Quickwit splits. So a split is one piece of the index, basically. So that data set 2 hours ago, it was I think it was 30 plus splits. And each split is it's pretty large. It's in gigabytes. So pretty quickly you get to 100 gigabytes, one terabyte, so on and so forth. So like I said, we have many splits, and that's great because right now we have like 3 leaf nodes, just like the diagram. So one of the node is going to act as the root node. So it's receiving my query, this query I'm typing. It's going to PostgreSQL, and it's asking for, okay, which are the splits that are relevant for that query? Because we have another mechanism that I did not explain, is each split is responsible for some time. So you can say, hey, if the split was created in the last 30 seconds, it's basically responsible for the last 30 seconds. So for that query, actually, I didn't use a time range. But if I were to filter on a time range, I would have less splits to query, so less data to download, less data to compute. But for that query, I did not do that. So the metadata level is telling you which splits are relevant.
And sorry, this will give you the turbo index.
It will not give you the turbo index. The turbo index is as part of the split. It's actually a footer. So if I come back here, the root node is going to say, hey, okay, let's just say there are 30 splits. So it's going to say, okay, I have 30 splits. I have 3 nodes. I probably should give like 10 splits to each node. So each leaf node is in charge of performing the request for for 10 splits. And then we use like a rendezvous hashing algorithm to make sure that there's some affinity between the split ID and the machine, so that if we redo that computation again and the same splits are targeted, then the same machines are going to be used. That way, like, caching is more efficient.
Okay.
So each leaf node is going to be responsible for 10 splits.
Okay, so if each node is going to take care of a portion.
Yes.
Okay.
So if I had only one node, then it would just do the work for like 30 splits. If I had 5 nodes, then I would do, each node would process 6 splits. So we try to spread the load. And
in terms of, I guess there are benchmarks to understand, depending on the size of the split, what's the best number of nodes?
So we try to produce splits that are always more or less the same size. So we're really getting into like the internals of Quickwit, but basically we run merges. So if the throughput, let's say like you have more activity during the day and less activity at night. So the splits during the day are going to be bigger. What we're going to do is the splits during the night, we're going to merge them together. That way we have less splits to process. So we have a sweet spot of number of documents per split. And so that drives how many nodes you want to have. But I actually like the main driver is like the bandwidth. For us, like if you tell me you can have like one instance with basically what we're trying to optimize is like the number of gigabyte of bandwidth per core. So we're not particularly interested in like huge machines with normal network interfaces. We'd rather have more machine that bring us more network. So I'm trying to find a good example for this. Let's just say I have the choice between two machines. Yeah, two machines that have like, I don't know, 10 gigabyte network interface and 8 CPUs, or two machines with 10 gigabyte network interface but more CPUs. I think you'd rather get more of those machines that are less CPUs but the same bandwidth, because the bigger ones are going to be more expensive, but they're not going to give you like more network. And actually, like Quickwit tends to saturate the network more easily. So we'd rather choose machines that give you like a good ratio of like compute power to networking, which I think is a like in Shen nothing, like network is important, but you're not optimizing for networking. You're more optimizing for like density. So you want the ratio you optimize usually is like, I don't know, memory per CPU, for instance, and we're more looking at CPUs per network.
Okay, that's really interesting. I like to ask more, but I feel like for now we already have a great
so I
overview.
I think at Quickwit we're pretty excited about this slide, because we just, as every time the network gets better, like every time the network gets 2 times better, Quickwit gets 10 times better. So we're really looking for, like, if you look at the machines available on AWS, like the smaller machines, they usually have a network interface that's not as great. It's like 10 gigabyte or 25. And then if you want a much stronger network interface, like actually like the ratio of like network gigabyte per CPU is actually not interesting. So really hoping that eventually like small instances will have like much better network, so we can do more efficient downloads.
So, okay, being this so communication bound, you are saying so I understand that the memory needs also to increase as you have more bandwidth, correct? The CPU, sorry, needs also to increase as you increase the bandwidth of your network.
Yeah.
But it's really the bandwidth that drives everything.
Yeah, basically we have a sweet spot where we have like, I don't know, like let's just say like 2 gigabyte by CPU. I don't know, it's just, and after that we'd rather have more cores and CPUs that just hiding network per CPU. I don't know, it's a different way of thinking when you're like mostly bound by the network.
It's still a map reduce model, right?
Yes.
So and that reduce is happening on the root node? Okay. So you're just favoring the more splits you have, the better. The more you split the data, the better.
Yeah, to a certain point, like at some point you do way more, you do too many requests, and then you can't amortize the latency with getting a chunk that's big enough. Like there's really no point going to paying like 50 to 100 milliseconds to get like a few bytes. So when you're going to cloud storage, it takes a long time. So you wanna make sure you went there for a good reason. If it takes like 50 seconds to go to the object storage, but it takes only 1 milliseconds to actually download the data, then the cost, the latency cost is not amortized. So it makes more sense for us to like download bigger chunks so that the cost of going to cloud storage is amortized.
And then from a cost perspective, I mean, the pods, those 3 pods, when you restarted them, basically they had to sort of hydrate their local cache of those little Quickwit.
We don't do rehydration.
Or they had to recreate, I guess, maybe the cache. They had to recache. They lost their in-memory cache.
Yeah, they lost it, and we don't do anything. We're just waiting for the first query. So
you build up the cache from scratch.
Yeah, so that first query is going to be more expensive.
So there's no like, because I'm thinking just of the scenario, because this looks like it's like partway on the road, on the journey. Like I'm just thinking about like if those nodes were functions, if it was really efficient and you really don't want to run them when you don't need them, they could be functions, but then you lose the fact that their memory, that their cache is in memory. Does it is there a scenario where they would work well as functions? And
I think there is. Sometimes we talk about it. We haven't done it, but there's normally our searchers should be able to run in lambdas.
You would have to keep the cache, I guess, somewhere.
They would
closer.
They would be just a little bit slower.
Or they'd just be slower.
Yeah, they would be slower because they would take the hit. But technically, we could do everything with lambdas. Maybe the aggregation at the end, like the merge part of the MapReduce, basically would have to do it on the client, I guess, because I don't think it's possible to connect lambdas together. So that would be a difference. But otherwise, we should be able to execute our search queries at lambdas. Yeah.
And so can you scale up your replica? Like right now you have 3. Let's say that you want to double that. So you go to 6. What should you do to gain an advantage? Do you need to go back to 0 and restart, or can you add on the fly? And then what would happen to what's already cached?
So you can add them, and we use rendezvous hashing to preserve the affinity. So I think you would have some nodes, like the nodes that were up before, some of them would still work on the same splits. Actually, I don't remember exactly what's the policy of like basically our routing algorithm. I think for the it's hard to say what's going to happen, because basically some splits going to have a little bit of data cache. Some splits are not going to the same node as before; they're going to a new node, so you'll pay a penalty. But at the same time, each node is going to process less splits. So it's hard for me to predict what's going to happen.
Yeah, it was more to understand if there is the possibility to do a scale up, or in general, and considering that anyway it was pretty fast, doesn't really, that was more a curiosity if can adapt at the scaling up, or if we need anyway to scale down and then. No,
you can you don't have to go down and then up again. You can always go up if you want, or go up and down and then up again.
This was great.
Yes,
Thank you
really
so much.
interesting.
Thank you.
Yeah. And we have a few people at this hour. We have one person left. So Santos, thank you for sticking around until the very end. We appreciate it. And thanks.
Thank you.
Thanks, Santos. Yeah, Adrien, yeah, this is it's really interesting, and that demo was it is impressive. Also, I didn't know about the GitHub archive. That's cool.
Yeah, it's a cool data set.
It's good to know that it's there. So yeah, we're really grateful that you came on the Cloud Native Meetup. And we're grateful that you're sharing all this information with us. We wish you the absolute best of luck with Quickwit.
Thank you.
And yeah, Gabri, any closing words?
No, I think you said it all. And as soon as we have the recordings ready, we're gonna post and share with you the link.
Okay. Thank you.
Thank
Yeah.
you.
Sounds great. All
Have a
right,
good
I'm gonna
night.
stop the recording. Good night.
Bye-bye.
Bye-bye.